Good day everyone. We are the Group 5 and today we will be discussing problem 3.52. Problem 3.52 states a thin electrical heater is inserted between a long circular rod and a concentric tube with inner and outer radii of 20 and 40 mm. The rod A has a thermal conductivity of 0.15 watt per meter Kelvin, while the tube B has a thermal conductivity of 1.5 watt per meter Kelvin and its outer surface is subjected to convection with a fluid of temperature of 15 degrees Celsius and heat transfer coefficient of 50 watt per square meter Kelvin. The thermal contact resistance between the cylinder surfaces and the heater is negligible. And the questions are: first, determine the electrical power per unit length of the cylinders that is required to maintain the outer surface of cylinder B at 5 degrees Celsius. And second, what is the temperature at the center of cylinder A? In the problem, we are given the thickness and thermal conductivities of the original wall, the insulation layer, and the glass layer. We are also given the temperatures inside and outside the walls with convection heat transfer coefficients. And we are to find the electrical power required to maintain outer surface at 5 degrees Celsius and temperature at the center. This will be the schematic diagram of the problem, and we need to have some assumptions which are steady-state conditions: one-dimensional radial conduction, constant properties, negligible contact resistances, and no generation. For A, we need to perform an energy balance on the composite system to determine the power required to maintain the temperature at 5 degrees Celsius. Since we assume that it is in steady-state conditions and no energy generation, energy stored will be zero as well as the energy generated. Then, using the Newton's law of cooling, and plugging in the values, we get electrical power required equal to 251 with M. For B, from a control volume about cylinder A, we recognize that the cylinder must be isothermal, that is T of R sub 1 is equals to T of 0. Then, we need to represent cylinder B by a thermal circuit as shown in the figure above. For the cylinder, it is given on equation 2.38. After rearranging and substituting the values, we will get 23.5 degrees Celsius. Therefore, the temperature at the center of cylinder A is 23.5 degrees Celsius. That's all for problem 3.52, and thank you for listening.